This is a video that I wanted to post to you all that illustrates the use of the complement rule. And hopefully up to this point you've read about the complement rule, but a form of it says that the probability of some event E is equal to 1 minus the probability of E complement. And as you study, the complement of an event is basically all the outcomes in the experiment that are not in that particular event. Okay. And we're going to apply this rule in this problem here. And so what's going on is we've got two six-sided dice that we're going to roll. And we're asking ourselves the question, what's the chance or probability of rolling a sum greater than or equal to 3? Okay. The event of interest is rolling a sum greater than or equal to 3, and that's the probability, or that's the event whose probability I want to compute. And so I'm going to be talking about that event a lot, so I'm going to let A be that event, that it is a sum that is greater than or equal to 3. The sum of the two dice is greater than or equal to 3. I'm going to let A be that, and just for notation's sake, capital S is my sample space. If you recall, the sample space is all possible outcomes of an experiment. Okay. Well, so what I want to do here is compute the probability of A. And up to this point, hopefully you've seen through some of the more basic probability problems, is that the probability of A is the number of outcomes in A divided by the number of outcomes in S. Well, let's see. The number of outcomes in S is really not too difficult to get a handle on. Now, the number of outcomes in A is a little more work. Let's see if I'm going to make a table here that will make this problem a little more digestible. Die 1, I'm going to say, well, we can roll 1, 2, 3, 4, 5, or 6. And I'm going to have on the rows here die 2. 1, 2, 3, 4, 5, 6. Now, what I'm looking at is all the pairwise combinations. Actually, the pairwise permutations. I need to be careful with that term. We will see that term in a little bit. But looking at those and looking at what the sum would be. Okay, so this first pair here, if I rolled a 1 for die 1 and a 1 for die 2, the sum would be 2. Let me draw a line here to distinguish. If I rolled a 2 for die 1 and a 1 for die 2, then the sum would be 3. If I rolled a 1 for die 1, a 2 for die 2, the sum would be 3. If I rolled a 2 for die 1 or 2 for die 2, the sum would be 4. And so you get the picture here. So right here I would have a 4. Here I would have a 5. Here I would have a 4. Here the sum would be 5. Here the sum would be 6. Well, so I have to fill in this whole table, and that would be 36 entries, and we could do that. But in getting at this probability, there's another way to get to it, and I'm going to use that other way because this N of A is let's see, cumbersome to enumerate. What I mean by that is it takes a lot of work to write out all the outcomes in that outcome. I'm sorry, all the outcomes in that event. So what I want to use is this idea that, well, the probability of A is 1 minus the probability of A complement. And this is again by the complement rule. Here. Let me move my paper up a little bit. And I contend that using this rule is a faster way to solve this problem than just computing it in the standard approach. And the reason is because when I think about what is a complement, well, off to the side here, a complement has got to be the event that the sum is less than 3. Okay, that's all the outcomes that are outside of this event, but that are in the sample space. Well, if I look at my picture here, now I know if I were to continue to fill in this table, I'd have my numbers would get bigger in this direction and so forth in this direction. But this outcome right here is the only outcome where my sum is less than 3. So when I think about a complement, it's the outcome where the sum is less than 3, but that's really it's the event where the sum is less than 3, but that's really just the outcome where the sum equals 2, namely where I roll the 1-1 dice combination. So when I come back to computing the probability of a complement, that's the number of outcomes in this event, a complement divided by the number of outcomes in the sample space. A complement, I've got it right here, the number of outcomes in that, well, there's 1. The number of outcomes in the sample space, well, if we were to go to fill in this table, you would see there's 36. You don't have to fill in the table to get all 36, but just know that you have 6 times 6 ways of having of casting the 2 die here. So this is 1 minus 1 over 36. So what we get is then 35 out of 36. Okay. And this is a use of the complement rule. Oftentimes we use it in the setting here, as we did in this problem, where the complement is easier to think about than the original event of interest.